Dear viewers, welcome to the class of Fundamental Chemistry. And today reactions are Negishi reactions and Heck reaction. This is part 3 of our organometallic compound series. So what is Negishi reaction? In Negishi reaction you can use wide variety of metal like organozinc, organoaluminium, organozirconium. In Negishi reaction, you treat your organozinc compound with organoelectrophile in presence of palladium catalyst. It will give you new carbon-carbon bond formation. And when we talk about reactivity of organozinc compound are much more reactive compared to organostenane and organoboranes. So organoborane, your carbon has electronegation 2.5, boron is 2.0, so electronegation difference is 0.5. And when we talk about organotin compound, carbon 2.5, tin 1.8, it will give you 0.7. But when we talk about carbon zinc organometallic compound, carbon is 2.5 and zinc is 1.6. So organo zinc compound has electronegation difference 0.9. So electronegation difference 0.9 is higher compared to 0.7 and 0.5. This is the reason your organozinc compound are more reactive. In organozinc compound, what R can be? Your R can be vinyl group, aryl group, alkynyl group, benzyl and alkyl group. And R prime X, your organoelectrophile. Your organic part can be allyl, benzyl, vinyl, aryl and alkyl. And X, the leaving group can be triflate and halides like chloride, iodide, bromide. So order of reactivity of organoelectrophile in case of Negishi reaction, it will be allyl. This allyl will be much more reactive compared to benzyl, and benzyl will be more reactive compared to vinyl, and aryl will be more reactive compared to alkyl group. So vinyl iodide, this vinyl iodide is reported to be 100 times more reactive compared to primary alkyl halide. So this is about the reactivity. Your organozinc compound is very reactive. So it is not stable in air and moisture. It can degrade very easily. So whenever we perform Negishi reaction in lab, we keep our glassware well dried and we use argon condition or nitrogen environment to perform this kind of reactions. Regarding stereochemistry, in stereochemistry you can see your organo zinc compound reacting with organoelectrophile. So this carbon will make bond with this part, okay, and your product will form. You can see here your product has same configuration as reactant. So there is retention of configuration. Also you can see your reactant has E and Z. Accordingly your product will have same configuration E and Z. The one point to be noticed here, your aluminium is in bond form with this vinyl part and alkyl part, primary. So this is isobutyl. So you can see in your product vinyl part is reactive. As I already told, vinyl is much more reactive than alkyl part. So this is the reason vinyl part is reacting, not isobutyl part. Other thing you can see here, sp2 bond is reacting with sp2. Okay, so you can make sp2 hybridized carbon-carbon bond formation. Okay, so in case of Suzuki coupling, Negishi coupling can even be used to form a new bond between two sp3 hybridized carbon atoms. If you take alkyl zinc and treat it with alkyl iodide, okay, you can get your sp3 hybridized carbon-carbon bond formation. So how you can make organo-zinc reagent? It is very easy. Just treat your organolithium with zinc bromide or your Grignard reagent with zinc bromide. You will get your organo-zinc reagent. Or you can use directly organohalide treated with zinc in presence of diethyl ether. You will get your Negishi reagent. Okay, so here you can see alkyl halide reacting with zinc, giving you Negishi reaction. So this carbon will make bond sp3 bond with other part, which can be sp2 or sp3. Sometime when you read research article, you will see in copper based chemistry, some people use zinc chloride or zinc bromide as an additive. So they use it to enhance the rate of reaction. Or there are some reaction without adding these additive zinc chloride and zinc bromide, that reaction do not happen. Okay. And mechanism of Negishi coupling. It is same as we studied earlier for Suzuki reaction, Steele reaction. So first step is common oxidative addition. Your palladium ligand complex, in which palladium is in zero state, which we known as active form of palladium catalyst, will go oxidative addition with organoelectrophile. It will give you first palladium complex, in which oxidative state of palladium will be 2. Okay, and next reaction is transmetalation. Now your organozinc reagent will come, in which organic part is on zinc. Now this will shift to palladium part and your X part will come out. Okay, so Z and X will bind with X, give you Z and X2, and R part will be shift on palladium. So this is transmetalation step, means exchange of metal. R is moving to palladium from zinc. And final step is reductive elimination. Your both palladium ligand will come out and R dash will make a bond, which is coupling product will come out. So this is the mechanism of Negishi reaction. Now we will study Heck reaction. In Heck reaction, your coupling part is alkene and organoelectrophile. So your R can be aryl, vinyl and benzyl, and X can be iodine, bromine or OTF. So your organoelectrophile is reacting with alkene in presence of palladium catalyst, and it will give you Heck coupling product. Heck coupling product. So your R is attaching on alkene. Okay. The reaction is more efficient when organohalide is iodide. Okay, so your iodine is much more reactive compared to bromine, triflate and chlorine. So what exactly the Heck reaction is? In Heck reaction, you treat aryl iodide with ethylene. You treat aryl iodide with ethylene in presence of palladium catalyst and base, and there is formation of new carbon-carbon bond formation. You can see styrene product is formed here. Okay, similarly, when you treat vinyl triflate with ethylene in presence of palladium, you can see conjugated diene formation, new carbon-carbon bond formation. So, because one part is alkene, which is sp2 hybridized, so there are formation of carbon-carbon bond between sp2 and sp2 carbon in Heck reaction. So this is sp2, this is sp2. This carbon is sp2 hybridized and this ethylene part is sp2 hybridized. When we talk about reactivity, so ethylene is much more reactive than monosubstituted ethylene. So whenever you increase the substitution, the reactivity decrease. Okay, and whenever we talk about substitution, this Z, if it is a electron withdrawing group, the reactivity enhance and the yield of product increase compared to electron donating group. So your electron withdrawing group can be ester, ketone, amide, nitrile and nitro. In monosubstituted product, so look at this reaction. Your organoelectrophile is reacting with this ethylene part. So this carbon can bind at this carbon 1 or 2. So where it will bind? So in this case, this carbon will bind at carbon 2, which is less substituted, and your product will be in E configuration. So in Heck reaction, your organoelectrophile will bind at ethylene having less substitution. Okay, this part having less substitution. Another thing to be noticed here, the new product which will be formed will have E configuration. So other thing, when you treat vinyl iodide with ethylene, you can see product has retention of configuration. So Z part react with ethylene, you will find Z configuration in your product. So this is retention of configuration. So two things. First, the new carbon-carbon bond formation will be trans substituted E, and if your reactant has E trans or Z cis configuration, it will retain in product. Okay, so mechanism of reaction. So mechanism, first step always will be oxidative addition. In oxidative addition, your organohalide will bind with palladium ligand complex, palladium having zero oxidative state. It will form palladium complex having oxidative state of 2. Now, this palladium complex, which is having R of organohalide, will bind to alkene. And how it will bind to alkene? It will bind in the form of syn addition, SYN, syn addition. Your R, this R and palladium, you can see they both are on same side. This is syn addition. Now carbon-carbon bond rotation will happen. Okay, so this bond rotation will happen. R will go on other side and palladium on another side. Okay, accordingly you can change the bond. Now R is in dotted form, and this methyl which was in earlier dotted form, it is in strong bond. Okay, so first step is oxidative addition, second step is syn addition on pi bond, third step is carbon-carbon bond rotation, and finally syn elimination of this hydrogen with palladium. You will get your palladium product having H and X and your Heck coupling product. Okay, so this part will give you this product having double bond, and hydrogen will come out with palladium. And finally the reductive elimination, base will remove this HX. Okay, and it will return your palladium zero oxidative state catalyst back. So one example we are taking of cyclohexene. When you perform Heck reaction with cyclohexene, you will see shift of double bond. Okay, you will expecting product like this, but you are getting product like this when you treating it with cyclohexene. So what is the reason for shift of this double bond? Okay, so when you treat cyclohexene with your organoelectrophile in presence of palladium, so we know first step is oxidative addition. Okay, so your organoelectrophile will bind with this palladium ligand. Next step is syn addition on this double bond. So you can see your R part will come here and palladium part will come this side. So both are in syn form. Now when we talk about syn elimination, you can see this hydrogen is on same side with this palladium, but this hydrogen is on another side which is far from this palladium. So the maximum possibility is removal of this hydrogen by palladium. So that is the reason your double bond shift occur when you perform Heck reaction with cyclohexene. So thank you viewers, this was about your Negishi reaction and Heck reaction. So I will give the link of part 1 and part 2 of organometallic chemistry in description box. Thank you.